Alright, hope you guys are ready to learn about the most widely used routable protocol on the internet, that is IP, also known as the Internet Protocol. Let's jump over here to the IP header structure. This is an awesome diagram that shows it very well. So, first off, there's a few important facts I want you to remember. And that is the minimum header size for the IP protocol is 20 bytes. The maximum header size for the IP protocol is 60 bytes. Do commit those to memory. Most of the time you'll be working with or seeing 20 byte IP headers, but there's an optional IP options field that can make the header longer. Also, the maximum size for the IP header is 65,535. So let's go ahead and move over to the Tcpdump or the terminal window so we can run Tcpdump here. And I'm going to go ahead and open up, first I'm going to use a -v option for verbose, which will print out extra information about the IP header fields. And then I'm going to read in a pcat file, so just do google.pcat. And then I'm going to use the -x option to print ASCII and hex data of the actual payload portion of the packet. And then, the entire IP packet. And then what I'm going to do is I'm going to print one packet to begin with so we don't clutter up the screen. So this field is what's added by the verbose option, the -v. It is the field that, or this line adds a number of different IP header fields and just prints them out for you so they're easy to see. So let's begin with the first byte of the IP header, beginning offset 0, and that is this byte over here. You can see this is 1 byte and there's 2 fields in this byte. So each of these fields are 4 bits, and in computer science, 4 bits is also known as a nibble. And the first one is the version number. And you can see down here it says the version of the IP protocol, 4 or 6 are valid. The next nibble is the internet header length. And this is the value of, or the value here is represented as 32-bit words, and it's used to describe the size of the IP header. It's how the operating system knows, or any device, like the routers, know how long the IP header is. And if you look over here, it's set to 5. So 32-bit words or 32-bit words are also equivalent to 4 bytes. So, which is 32-bit divided by 8. What this means is we can actually multiply this 5 here by 4, and that equals 20. And that actually means that this is the 20 byte, this IP header is 20 bytes in length. So this is actually how we know how the size of the IP header. Now, if we have IP options enabled, this particular nibble will be larger. And we'll show that later. The next field is the type of service. That's also shown up here, TOS, and that is now known as differentiated services, and it's used for quality of service and latency and stuff like that, setting particular bits that routers and devices are programmed to read in and decide whether to transmit faster or something like that. So just a way to provide priority on packets. And then we have the field after, which go ahead and refer back to the diagram. This is this total length field. This is a 2-byte field. And this particular 2 bytes is the total amount that, or is the size of the IP header and its data. We refer to that as total length, and that is different than the header length field, or the internet header length field. That's one way to clarify those two, is that this one's just of the header length, and this one's just the size of the IP header plus the data, it's the total length. And you can see that if it's 2 bytes, that is 2 to the 16, because 2 bytes is also 16 bits. And that means there's 65,535 possible values, or 36 possible values if you start from 0. And the biggest, like I said earlier, is that the maximum packet size for IP can be 65,535. So that's where this comes in. This is how that's determined. Next, we have the IP identification field, an IP flags field. The identification field is actually used for fragmentation, which we'll also talk about later. Also, we have the IP flags field. Remember, TCP, or you may or may not have known, but TCP has, if you didn't watch the other videos, has its own flags field that specify what the segment is supposed to do. And this one has three different bits, 3 different options here. So the first one is the reserve bit, this X, and it is not really in use. There's a humorous RFC that went around that refers to this bit as the evil bit, that if this bit is set, then the packet must be evil. It's kind of funny, but you can check it out. The next bit is the don't fragment bit set. Don't fragment bit, and that means that the router should not fragment this particular packet into smaller pieces. Then this one's the this is the more fragment bit. And that's just a way to say, hey, the more fragments are going to follow. Then we have the fragment offset field, and this is a way to refer to data after the IP header relative to the beginning of the first fragment, so that during reassembly they can all be put together in order. Then we have the time to live field and the protocol field. Let's go ahead and go back here. So we're actually right here now if we count over. The time to live field is 40 here, and we do printf and print that in decimal. 0x40, that is 64. And if you look at the top here, TTL for time to live is 64 when TCpdump translated it with the -v option. And the time to live field is a field that using a number describes how long the packet should live, its lifetime. And it does this by, so we started out at 64, which your OS sets. Different operating systems will set different numbers, but in Linux it's common to see 64. Once the packet hits the first router, say my home router, it'll be decremented. At 64 will be decremented by 1. It'll then become 63. And for each router that it hits, it'll be decremented by 1. And then when it gets to 0, it becomes discarded. The router throws it away. And the reason we have this is to prevent routing loops or packet loops, actually. So we prevent these packets from having this never-ending cycle where they just route throughout the internet. So this is how we put an expiration time on packets. Next, we have the IP ID field. Here's a translation right there. Oh, I'm sorry, not the IP ID field. We were right here. So we have another field, and that is at the 9th byte offset, I believe, or the 10th, and that is the protocol field. So if you go back here, so we have 8. Oh, no, that is 9 byte offset right here. And this is a field that tells the operating system what kind of protocol IP is carrying above it. And if you take a look here, we have 06, and we can do grep TCP. So I know this off the top of my head, so I'll just show you. 6 is TCP. And you can see over here that TCP already took care of that and showed you that it was 6 up here with the verbose option. And it translated that to proto TCP for you. So after that, we have the header checksum field. And this field is used to perform a checksum on the header, and if the header checksum fails, then the packet is discarded. So it's a way to validate or keep the integrity of the packet and lets the router or the host know that it's been tampered or damaged or something. So that's just a way to verify that. Then we have two fields after, which are the source and destination IP addresses, and we all are familiar with those. All right, so now let's talk about an IP option. So first off, what I'm going to do is I'm going to begin capturing on my interface for packets that match the criteria of IP and ICMP. I'm going to background it. And then I'm going to go ahead and use ping to use a record route, which is a type of IP option. And we're going to say, hey, only do one packet, and then I'm going to give it an address here. I'm using my local router. Okay, sent the record route, pull it from the foreground, quit that. Now I have a pcat file that has that information in it. So we go to ip.pcat, read that in, and you can see we have 2 packets here, and they look like normal ICMP when you use a ping, that is normal ICMP echo request and its reply. But there's more to it here. We use the -v option and the -X option. The V will print more IP header information in this case, and the -X option will print data from Hex with Hex and Ascii of the data in the packet. Okay, so we're going to stop here. We're going to go over to the internet here and type in IP options. Let's go to the first link from IANA. You can see here that says the Internet Protocol has provision for optional header fields, and there's actually quite a few of them. So we're going to be specifically talking about record route, which is an old one, not really used anymore. A lot of these aren't really used at all, and we probably won't encounter them, but you should be aware of that this is a field in the IP header and that can make IP do different things. Two that might be concerning is the strict source route. Anything that matches source route, let's just do that. So we have strict and we have loose. This is a way that someone can craft packets that only follow a particular path. That is, they hit the routers that they want because they set the source path in the packets. And this was a security concern many years ago, and it could be still today, but most routers will drop packets that are not allow them if they have the source route options enabled. Be aware that can be it could be still an issue. So now we're going to go back to this IP datagram. And we see it's an ISP echo request. And then what we want to do is really want to show, what we're trying to do here is show you, how do we know that IP packet contains options? Well, we talked about the internet header length earlier. We're talking about that again right now. So remember, the first nibble, first 4 bits is the header, the version number. The second nibble in the first byte is the internet header length, which is the number of 32-bit words inside the IP packet. And if it's set to 5, you multiply that by 4 because a 32-bit word is equal to 4 bytes, and 5 times 4 bytes is 20, meaning the minimum header size, or meaning the packet's header size will be 20. However, this is F. And F in hex is 16. Or 15, sorry. That's right. So what this means is, this would be 16 if it would start from 0. What this means is, this packet has IP options enabled. So we take that 15 and we multiply it by 4, and that we get 60. So just to verify, 15 times 4, we get 60. So that means we have the 20-byte header, and then the rest of those bytes are the actual IP options. So here we have 16 bytes. We start at the 18th. Here's the 20th byte offset. And then after this is all the IP option stuff. So what record route does is it's like a precursor to trace route almost. It's a way to keep track of every route that your packet makes it to. And those routes are then stored back in the IP packet. You can see here when we use the -v option, it translated, it found it, and it printed the options field up here. And it said, hey, this is RR, which means this is a record route packet. And here's the places it traversed, which are then stored inside this packet. So what we can, or if we go back to let's go here. Actually, let's go to a more detailed guide. I actually wrote one a long time ago. Let's try to find that real quick. Go to my website here, search for IP. Oops, search for options. All right. It's one of the first articles I wrote, I think, when I was in high school. Or, no, a few years after. But this packet actually details the source strict routing, loose strict route, source routing, and record routes. So do check this out if you want to know more about it, which I do recommend learning. So you can say that this particular part, after the basic part of the IP header, that is, once we get to the end of the destination address, here we have the IP options. So there's a number of different smaller fields in the IP options, and then the data after that. So we have this byte here, and then we have the length, a pointer, and then the route data in the terms of the record route. So one thing to note here is that the size is 60 bytes of the header, and that a IP address is only 4 bytes. And if it stores, if the record route tries to store each router that it passes inside the IP header, then you're going to be limited on the number of IP addresses that are going to be available to be stored there. And that's one of the reasons we actually went to traceroute, because it didn't use that technique. It was able to do longer paths. So in our case, you can only store 9 bytes. Let's see if I have here. Yeah, so I wrote about it. So you can only fit 9 total IP addresses in here. So we'll have 37 bytes left. So we won't actually be able to fill the 10th IP address. So 4 times 9 in this case is 36 bytes. And if we go back here, you can see that, how many do we have right here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we filled all of the 9 placeholders for the record route. So those are 4 bytes apiece, each one of those. And you can't do any more than that. So again, there's a lot of stuff with these IP options, and I always forget this stuff. I have to review it from time to time. I just did a quick prep here, pretty much live though, for this video. But I do recommend, if you're interested in these things, to do take a look further and let's quickly look at IP fragmentation. So I'm gonna go ahead and start sniffing on my ETH1 interface. I'm gonna generate a PCAP called Fragment.pcap. I'm gonna specify a filter for IP packets and match IP packets that also are carrying ICMP. Go ahead and use sudo so I can sniff on the, open a socket there. All right, now we're gonna actually generate our own fragmented traffic. We're gonna use ping and say, hey, you only send 1 ICMP echo, and then we'll specify a byte size of 2400. So this is the size of the packet's gonna send. You actually need something larger than the default maximum transmissible unit size of Ethernet, which is 1500 bytes by default. So if we can take a look here, MTU, you can see that it is 1500, so something larger, and 2400 bytes is larger. And I'm gonna go ahead and print out my, or use my router. Okay, so let's go ahead and close that. And let's go ahead and open up Fragment.pcap. You can see here we have a few different packets. We have 4. We have the ICMP echo request right here, some strange packet that's going to the router. This is IP proto 1, the ICMP echo reply, and also some strange packet that's coming from the router to me. This is proto 1 again. Remember, protocol 1 is actually ICMP. So if we just do grep ICMP, see protocols, you see that it is 1. So what's actually happening here is that when fragmentation happens, the header is in the first packet. The other packets do not carry, the other fragments of that particular group of fragments does not carry the ICMP header. It carries the IP header, of course, it has to, but not the one above it, if it fits in the first one. So that's why Tcpdump is not able to figure out what is actually carrying, but it is related to this packet. And we know this because let's have the -v option to print out more information here. And that is because of a field called the IP identification field. If we take a look at this field right here, and fragments that are a part of the same packet, that is, you have a large packet, it is broken up into fragments whenever there's fragmentation. When it's both broken up into fragments, each of those fragments contain the same number to refer to that one packet, that larger packet that was broken up. So that's how they're grouped together, so that when the receiving host sees it, it can put it back together. So anything that has the value 2,489 or 20,489 will be a part of that one big packet that was split up. So these are 2 fragments that are a part of the same packet, the same original packet. And you can see that under the flag setting, the plus is set, which is actually refers to the more fragments field. And this is set whenever there are more fragments to come. And you can see this matching one that matches that one, it's part of that same packet that was broken up, now has none, because the last packet or the last fragment does not have more fragments coming, so it's not set, and the value is typically none. So in this particular case, we have a length of 1500 bytes, the MTU, and then if you add 14 for the Ethernet header, then that's 1514. But when we're referring to the 1500 bytes, it actually the 14 bytes are not counted in that MTU. So 1,500 there, which is the max that we could send. And then we have the remaining amount, which is 948. And we'll have to do some math here because that doesn't, if you add that up together, it does not equal 2,400. But I'll show you kind of how that works. So let's go, first of all, before we even do that, let's take a look at this with the Hex and Ascii view. And you'll notice how just a lot of data here. And that's because we stuffed so much in a single packet. And also one thing that's kind of interesting to note is that ICMP records the same, has its own little signature for ping, or for echo. And just over and over, you'll have that same string of characters. Something to note. Now, what we can do is, we'll show you the length. Let's do the math on those length here. So let's go back here. So we have 1,500 bytes, and we see that right here at the length, total length of the IP packet. And we have the total length of the other IP packet, or the fragment that's associated with the first one. And what is that? That's 2,448. Well, we subtract 20 bytes from the IP header for the first packet. Then we subtract 20 bytes from the IP header from the second packet. And then we have 2,408. If we scroll back up to the ping, there it is, the 2,408 bytes that were sent. You can see it has the 2,400 right there, and then 2,428 here. And this is referring to the IP, or the header, and then 8 bytes for the ICMP header. So if we actually subtract 8 here, which is the size of the ICMP header, then we have 2,400 bytes, and that accounts for all those bytes that were sent out when we use the -s option of 2,400. Okay, and there's more to deal with that you can look up for fragmentation, because there's Tcpdump. When you have more, it'll be able to calculate the offset values and stuff like that, so you can figure out where the data starts relative to the first fragment, and etc., or relative to the first packet, etc. So for more information, do look that stuff up online and get comfortable with it. Thank you.